So thank you everyone for coming, and thank you for the kind invitation to talk to you guys. So I will try to keep it simple, and it may be erring on the side of simplifying things too much. But again, I'm not always very good judge of um, how things. I don't need a clicker. It's fine. So if something is not making sense, please feel free to stop me. I don't have an agenda to finish, all the slides. So I would rather, since, there are not too many AMO folks around on campus here, I would rather give a talk that's, partially gets through to everyone. So I can stop at any time. So just feel free to interrupt me. Okay. So there are people on the campus here who work in ultra-fast science, and I think that idea is fairly simple to explain. If you have a very fast motion, faster than your eye can resolve, for example, the seams of this basketball, yeah? So if you want to resolve that and understand it as it's bouncing very fast on the court, your eye is not fast enough to do that. But you can use a strobe of light, a flash of light, yeah, and you can take snapshots at different instants of time. And as long as the flash of light is shorter in duration than the duration it takes for the ball to move from here to the next position, you have essentially frozen the ball in time during that snapshot, right? Because you took a picture at an instant by shining photons on that ball and collecting them before it had a chance to move, right? So you got an image at that instant. Then you send another strobe, a flash of light, a little bit later, another strobe, a little bit later. And if you put together all these images together, you can have a movie with very fine details being captured in each snapshot. So this is the idea behind ultra-fast science. You want to capture fast motions by using flashes of light, which are faster than the motions or commensurate with the motions. Okay. So for macroscopic things, having millisecond or microsecond resolution is good enough. But for quantum world, it's not good enough. There are no electrical techniques or electronic techniques by which you can strobe things fast enough. If you want to study the motion of molecules, for example, the molecules, for example, nitrogen all around you has a rotational motion which takes picoseconds to execute, right? Which is 10 to the power minus 12 seconds. The vibrational motions takes tens of femtoseconds. Femtosecond is 10 to the minus 15 seconds. So for those motions, you need flashes of light, which are on those timescales. To make those flashes of light, we need lasers. We need a lot of colors which are in phase, arrive coherently to make a short pulse of light, right? So the invention of lasers in 60s opened up that game, that we could take real-time images of quantum motions. And these things became quite commercial in the 1990s. You can buy the laser from supplier and start doing your condensed matter, ultra-fast science, or physical chemistry, or atomic physics, yeah? But the electronic motion was out of reach because, as Robert mentioned, the electronic timescale is much faster than the vibrational or rotational motions. It's an attosecond timescale. And this is not in any quantum textbook, because in quantum textbooks, you always talk in terms of energy levels. Yeah, and when those things were devised and written, people didn't imagine that one day you will have light pulses of attosecond durations. So the question of timescale is rarely raised in quantum textbooks. But with any two transitions, there is a frequency associated. So there is a timescale associated with that. And if there is a complex electronic process where electrons are jumping around, talking to each other, you can now use attosecond light pulses to resolve it. and I think Robert mentioned that the Bohr orbit timescale of electron in a hydrogen atom is 150 attoseconds. Yeah. And nowadays, people have succeeded in making pulses of light, which are well-controlled, nice pulses of light, which are 50 attosecond, right? And the field is still evolving, so you could go even faster. The way we do it, and I'll just give you a superficial slide here, is that we take a light pulse and we gang up a lot of photons from this laser together to produce an X-ray light pulse. We just nonlinearly combine tons of photons, yeah? And then we have enough bandwidth to make a attosecond pulse out of it. And I'll come back to this later. So maybe for now, you just believe me that going to X-rays makes it easier to produce attosecond light pulses than visible. Because in visible region, you need to capture all the colors from UV to infrared and compress them together. You know, large delta E makes short delta T. So you need too many colors, right? For a given optical frequency, you need too much bandwidth. But in X-rays, it's easier because the frequency is so high and the wavelength is so short that you can compress few cycles within an attosecond, right? So our strategy, and a lot of people in this community, their strategy is to use these attosecond light bursts to not just measure these ultra-fast quantum dynamics, but also use these light strobes to control, right? A flash of light hitting the basketball is not going to do anything. But if you hit a flash of light on an electron doing something, you may alter its trajectory. So you can change its path, you can make it do other things. So that's the second aspect, which I will start out with, the control of quantum dynamics. Yeah. But before I start, let me just show you a visual picture of what I mean when we are strobing things. So this image, without any details, this is an image of electron waves coming out of an atom. In this case, I believe it's an argon atom. So you can see that there is angular distribution. There are these waves coming out. Each image is taken like 1 femtosecond apart. So you can see some things are changing as a function of time. The energies are changing and the distributions are changing from here to here. So this is just real space image, X and Y. Electron waves come out and hit our detector, right? So this is the kind of movies we develop, similar to the basketball analogy, where we take images every femtosecond and then we put it together to understand what's going on in the atom so that the electron waves are coming out like that. So this is the work that was done by my students. And then they stitch together all these images and they make spectrograms with energy information on one side, which is the radial axis here, and the time information on the other side. And you can see this is a wave packet that's beating in time. You can see these beautiful beats. And as a function of energy, you can see many different states beating together. So this is a quantum wave packet that's beating. So I won't go into details of this study, but you can look up this paper here if you're interested. Let me go back to the basics again and think in terms of what is taught in the textbooks. Okay. So what is time dynamics, right? So time is not an operator in quantum mechanics. What we do is we take a Hamiltonian, and if we are lucky, we can diagonalize it. And the energies, these eigenenergies, tell us about what dynamics will occur, because your wave function has these energy-dependent phase factors, right? I believe if you take first year of quantum, you will get to see this if you haven't seen it, right? If you're an undergraduate student. So, so these energies decide how the system will evolve in time, right? So if the Hamiltonian is fully diagonalizable, you can bring it in this form. The time dynamics is actually trivial. It's just some dephasing and rephasing of the wave packet. It's not super interesting. So the real stuff actually happens when the Hamiltonia are not simple, which is actually a lot of times the situation, right? Most of the times the situation. And the complication comes because the electronic states are coupled together due to the fact that in a many electron system, electrons talk to each other, right? You no longer have single electron system. Or the electrons talk to the nuclei, which means that when you give the energy to electrons, they exchange it with nuclei. And that leads to couplings between these states. You can also have light field, which can mix these states. And often in atomic and molecular physics, and also in condensed matter physics, you end up with the mix of all these interactions. So it's very complex dynamics. And that leads to Hamiltonia, which look like this. So you don't have a clear path on how to diagonalize it because you don't know these coupling terms, these off-diagonal terms a priori. That's why we need experiments, because in many cases, you don't know how to go ahead and find these off-diagonal terms. So we do experiments, we compare with theory, and the idea is to quantify the dynamics that stems from these kind of situations. You do that by basically finding these terms and rediagonalizing the Hamiltonian so that you have good understanding of the time dynamics. Okay. Any questions so far? Okay. All right, so then I'll give you a little roadmap of what I'm going to talk about today. And again, I don't have to go through all this, so just don't hesitate to stop. Yeah. So the first I'll talk about how the light field couplings, you have one state, if you use a light field to couple to nearby states or to continuum, and I'll explain these terms, how you can use that to alter the natural dynamics. Then I'll talk about how an electron packet moving around on nuclear potential energy surfaces, how can you measure that? And finally, the big problem which we are trying to attack at CXPEL and in my lab is how to understand electron correlation-driven motion of charges in molecules, because that is the fundamental underpinning of all the physical chemistry and biochemistry that results from photoexcitation. You give the energy to electrons, they interact with each other, and that's what leads to dynamics, right? So we will talk about this, but let me first pose the first question. Sorry, let me go back. So I will go back to this, but there is something called an autoionizing state. And it's created when you pump too much energy into your system, your atom or molecule, and this energy is more than what's needed to ionize the system. But the system still does not ionize. It just sits in some state which is ready to ionize. It's called autoionizing state. And this state can autoionize on a very fast timescales through electronic interactions. And I'll explain it in just one more slide. So let me explain to you the goal first. The goal is to find a way to use the light to shut down this process. It's a natural process. It's an unstable system, right? It's non-equilibrium system. How can you control this so that it does not autoionize? So how can you create entangled light matter states to stop this process using your light waveforms? So this is the work that was done in my lab a couple of years ago with my students here and in collaboration with Luca Argenti's theory group at UCF. And now let me explain what I meant by autoionizing states. And we'll walk through this particular example somewhat carefully. So this autoionizing state corresponds to a situation where you have high energy photon, and these are some electrons distributed in some orbitals. And the photon energy is high enough that if you remove the outer electron, the system will ionize, right? But if you remove the inner electron, the system will not ionize. It'll find some metastable, temporarily stable configuration. It's the inner electron that we are attacking here, right? So if your photon energy is greater than ionization potential, and if it's a many electron system, this is one of the possibilities, right? It won't happen in hydrogen atom because it has only one electron, but it can happen in many electron systems. Now, this is an unstable configuration. The electron here would like to fall through here and fill this hole, right? And then the electron that was excited ends up appearing ionized. So it's automatically becomes free. When the hole here gets filled, the electron over there is above the ionization threshold and it appears in the continuum. That's what this arrow means. So this is an autoionizing state, and this is the continuum state. And this process is mediated by the electrons talking to each other and rearranging themselves, right? So this is the process which is called configuration interaction, where two different configurations are interacting with each other and the electrons are arranging themselves. So we can now ask questions, how much time does it take? And people have explored it, right? And I will talk about how do we control this process. Any questions on auto-ionization? It's definitely not in undergraduate quantum texts. So, okay, so going back to the state, I call it bright state because we are exciting it with photon. So we say it's bright state. And it can decay into the continuum because it's a stable configuration. And this happens in atomic physics a lot. When the first spectroscopy experiments were done in early 1900s, people started noticing something strange in spectroscopic data. You expect the line shape to be Lorentzian, right? If you have an oscillator, which is what these excitations are, they are oscillators. And if you Fourier transform an oscillator, simple harmonic oscillator, you'll get a Lorentzian. But people started noticing that you had funny line shapes in your spectroscopic data. Energy versus cross section showed asymmetric line shapes. They were wondering, what is that? So Ugo Fano, Italian physicist, came up with an idea to explain this. He said it's actually an interference between two pathways to the continuum, one directly ionizing it, remove the outer electron. Other is you go to a bound state, metastable state, and then decay into the continuum. Interference between this and this results in a funny line shape, right? It's called the Fano line shape. And this is a formula for the line shape. He wrote a paper in 1930s and no one noticed it much, yeah? So he rewrote that paper in 1960s again. Now this paper has like, thousands and thousands of citations. Everyone understands Fano line shapes because of this physics, yeah? And they're very common line shapes in condensed matter physics, in all fields of physics. So our goal now is to control this process. And I will see that control through changes in the line shapes, through changes in the spectra of the system, right? So, so what we'll do is that we will bring a laser and tune it so that I create a coupling between the level E1 with another level E2, which now has to be a dark state. The reason it's dark is because it has the wrong symmetry. So you cannot excite it from here, but you can excite it from this bright state to dark state. Yeah, it has to do with the fact that in quantum language, the selection rules say that delta L equal to 1 for one electron excitation. So if you do that, you can reach this state. With 2 photons, you can reach delta L equal to 2. So you can reach the odd and even symmetries. Anyway, I'm digressing here. So you can use a photon to couple a dark state with a bright state. And what that does is that this strong interaction rediagonalizes the Hamiltonian. And I'll explain it in the next slide, how that happens. But that Hamiltonian that I talked about a few slides ago, it has off-diagonal elements. And you can rediagonalize it. And you'll find that this state and this state, they both split into 2 states, which is called Outler-Towns splitting. It's a phenomenon that's been known since lasers were invented and used to do spectroscopy. And I won't go into that. Maybe you just believe me that the lines will split when you resonantly couple them with the laser field, right? So these lines split, and now each one of these split lines can decay to the continuum. So do we see this in the experiment? Yes. So here is the data. The blue line is when I shine my attosecond XUV pulse train on the atom. I see that Fano line shape. But if I use this control laser field, then I see that the line has split into 2 separate Fano profiles. It has split into 2 absorption peaks. And so we were like, okay, well, this makes sense, but that's not surprising. It's expected from light matter interaction. The bigger question was something that was predicted 40 years ago. And this was by Zoller in 1980s. They had considered a similar problem theoretically. And the idea was that if you have 2 states which can both decay into the continuum, and if you can resonantly couple them with your laser light, you open up new pathways for interferences. Yes.
Each one of those lines is still followed by ionizing.
That's right. They are still many electron systems. They're still unstable, but the action of light field, the light field is short enough, is that it just splits the spectra into two parts. Yeah? But they're both autoionizing. So they both have this matrix element, which is off diagonal term. But if you bring a laser field, where one photon exactly fits between these states A and B, then you open up new pathways. And you can think of them like that. One photon can excite these states back and forth, but also the same energy photon can take this state and put it into this continuum, this state and put it into this continuum, right? It's a one photon spacing still. Energy spacing is the same, right? So now you have two ways to get into the continuum. You can naturally decay, wait for the electrons to talk to each other, or you can use your second photon to take this state to that continuum. Now that means there are two coherent quantum amplitudes to one final pathway. If you use this light field correctly, you can set up things so that this pathway and this natural pathway can destructively interfere, which means you can shut down the ionization or you can stabilize the atom against the ionization. So that was the idea, and but it wasn't verified. So we went ahead and looked into it. So I'm going to walk through some entangled light matter states here. So it's okay if you zone out for a bit, if if this is too much, but it's for experts, I guess. Yeah. So the idea now is that we have a standard Hamiltonian H0 with the electron-electron interaction here. Now I'm putting a lot of photons on the system. So I have a radiation Hamiltonian and I have a light matter interaction Hamiltonian. So my states are no longer just the matter states, which are these, but also the photon number states. So I have a direct product of matter state with a photon number state for both states, alpha and beta. So the beta state here, it can be represented as the matter state minus one photon. So I say n minus one here. So I'm trying to model this splitting by saying that one of them is n photon state and the other one is one photon dressed version of this state, right? So it's n minus one photon state. So, but these are not eigenstates. As I said, there is interaction because of this resonant coupling. So I have to find new eigenstates, which are superposition of these eigenstates with some mixing factors, okay? Which is basically I'm transforming from one basis in quantum mechanics to another basis with some mixing factors. So these things, these new states here that you get in a light field are entangled light matter states. The entanglement is defined as when you have two entities, but you write a wave function that cannot be separated into wave function of one times the wave function of the other. It cannot be separated into two parts. So you see here, I cannot write it as a matter state multiplied by a photon state. It's mixed together. I cannot write it into two parts. So it's an entangled state. So these are called polaritons. And in technical language, this is what is an extended version of a Jaynes Cumming model, which is used to describe the dynamics of atoms inside cavities when they're interacting with photons in the cavities. Yes.
Yeah.
Yeah.
Actually, typically, when people talk about polaritons, okay, the idea that the light matter interaction is strongly enhanced through the cavity, photons bounce back and forth.
Sure.
Gas phase, if you just have a single pass, you just get your dipole cross section. So up by.
No, I don't think even that is a requirement. I mean, the physics is valid. You can still apply those ideas, no matter the dipole strength. This is always correct. True. Definitely, this is always correct. You can write in terms of photon number states, and you don't gain any new insight yet here. It just simplifies the way we think of these interfering pathways. So it's not something that this only happens in this particular experiment. It basically is anytime you have a resonant coupling with two states, you can talk in these terms. Okay, so what we do is we can take one of these states and write it in terms of its components. So I call them AIP states, auto ionizing polaritons, yeah, which is again a simple matter of recasting what we already know about light matter interaction. But now I can now talk in terms of the fact that each of these states has two components. So in the case, in our experiment, those two components were determined by the two states we were using. We were working with argon system, which had a electron excited from 3s state to the 4p state, and it was coupled to the nearby state, which was a 3s electron excited to the 3d state. So I call them 4p and 3d components instead of alpha and beta. So this is the 4p with n photons, 3d with n minus 1 photons. And the 4p can decay to the p parity continuum, and the d can decay to the d parity continuum. But with my light field, which is a radiative ionization, I can decay to the opposite parity continuum, right? So this is autoionization, which decays to the same parity continuum. This is radiative ionization, which decays to the opposite parity continuum. The interference between these two can be written in terms of the amplitudes of interference of autoionization and radiative ionization and these mixing factors, yeah? So the overall rate of decay, the inverse of which will tell you the lifetime of decay, can be written in terms of these two amplitudes. Our job is to control these amplitudes. So I'll just try to convince you that that control is possible. So over here, I show you that this splitting here of the 4p line into two actually leads to change in its width. If I tune this field, this coupling correctly, this path, this width is narrower than this width here, and this width is also narrower than the original width when I had no light field present, right? So I have changed the width, delta E, which means I've changed the lifetime delta T of these states, right? So this is now longer lived state, which means it's an evidence of stabilization. The Jaynes-Cumming model shows you the same behavior here, that as a function of time, when the light field is overlapping with your atom, one branch becomes much narrower than the other branch. So there's a stabilization effect here. So we can now do it more systematically. This is our experimental setup. What we do is we take our laser pulse, split into two. One part is used to produce these attosecond pulses or pulse trains. Other part is used to control the atoms here that are excited by these attosecond pulses or pulse trains. So we use this as a control tunable field. Then we block this control field, this green field here. We let the attosecond pulses or the X-rays go through, and we resolve it spectrally, and we look at the spectrum. When the spectrum changes, it splits or it becomes narrower or wider, we can find that answer, take a ratio of output spectrum to the input spectrum, and then we can plot that as something called optical density. So we are going to try to control the absorption here. It's kind of a dense slide, but we don't have to understand every aspect of it. I'll just point out what's the main key message here. I want to use my laser wavelength tuning to control the mixing angle that goes into this overall rate of decay. And I want to use my time delay or intensity to control the radiative ionization rate, which is this over here. As a result, I can control the net decay rate of the atom. So we achieve this here by doing this experiment several times over at different laser frequencies. Each panel is a different laser frequency. And x-axis in each panel is time delay between the attosecond excitation pulse and the control pulse, because they're delayed in time. So there is an axis where you can represent that information. Y-axis is the energy of the XUV light, which is our attosecond pulse spectrum that we are spectrally resolving here. So, and then we are going to change the frequency of control pulse and see what happens. So what you see here is that the blue feature here is our absorption line, the Fano profile. And you see that it dips down here at this frequency. Over here, it goes up. And that's because of the fact that when I use this frequency, my dark state coupling, which is the laser dressed state, pushes this state down. When it splits into two or repels it, it pushes it down here. On the other side, when I use a high frequency photon, the one photon dressed state comes from below and it pushes it up. But if I'm resonant at this frequency, I split this blue line into two parts, one at the above, one below. So now I have a splitting into two polariton branches. One is broader, one is narrower. So this branch is broader and this is narrower, which is what I was demonstrating earlier. Essentially, that data that I was showing you earlier is a line out of this data along vertical axis. X-axis was energy and y-axis was amplitude. So, the theory models this and shows the same behavior. It's a full ab initio calculation. But coming back to quantitative comparison, when we take the line outs, we see that there are two polaritonic branches and the width changes with time delay, intensity, and other parameters. We can fit them with the Fano formula, okay, and extract the lifetimes. So, and I will just show you the results of the lifetimes here. So you see that left-hand side is experiment, right-hand side is theory. You see that at larger positive time delays, there is two lifetimes which are similar. But when you come to minus 10 femtosecond, one polaritonic branch gets destabilized because it has a larger energy width. Other becomes stabilized, which has a smaller energy width. So you're seeing this effect of light changing the lifetime, natural lifetime of the atom. And you can extend this idea to atoms, to molecules. You can say that you are using light to control the metastable states. If you're working with some chemical system and your product is unstable, you can use light to hold it there longer. You can control its lifetime, okay? So I'll skip some of the details here. The idea here was to say that it's not as simple. The reason I didn't make the lifetime infinite is because it's not just two states that I'm talking about. There are many states, and they each get dressed. So there are different kinds of couplings. So you have, when you take the full complexity into account, you find that you never have a complete destructive interference. You can control the lifetime, but you can't completely make it infinite. You can't prevent the atom from decaying. Eventually, everything decays, right? So, so we dug into that, and we understand this theory really, really well now. But I will pause here, and I think I have 10 more minutes. So I'm going to basically try to give you a gist of the two topics. And I definitely took a lot more time than I expected on this, but that's okay. So I'm going to try to now motivate what we are doing next and why. So if you have any questions on this so far, feel free to raise it. It's 50 femtosecond long. Exactly, because autoionization happens on 10 femtosecond time scale. If the laser field was not present, you can't exert control. So we had to actually use a longer pulse there. The ionization step and the excitation steps are pretty fast. Okay. So the second part of the talk is about electron nuclear couplings, which produce off-diagonal elements. And I'll just tell you why these are important. So in atoms, you understand the energy levels, E1, E2, E3. In molecules, the energy depends on where your atoms are. If you take nitrogen molecule, if you pull the nitrogen atoms apart, the energy changes. If you bring it together, energy changes. So energy depends on the internuclear coordinate, right? So as you change the coordinates, the energy changes. And if you have many electronic states, sometimes you can find a situation that the curves intersect. And if it is if it's not a diatomic and it's a polyatomic molecule, you can do different kind of atomic positions. You can adjust the angles, you can adjust the stretches. So you get surfaces now, surfaces of energy, which are obtained by changing your nuclear positions, right? And at some positions, these surfaces can intersect. So these surfaces are obtained under the assumption that nuclei are heavy. They don't move fast. Electrons are very fast. So we will just consider nuclei as frozen, solve the electron problem, obtain the energies, yeah, and then plot them, move to a new nuclear position, obtain the energies, and plot them. That's called Born-Oppenheimer approximation. But when you come to these intersection points, that approximation is no longer valid. And the reason is that your energy gap becomes very small. So the electronic timescales become long because delta E is becoming smaller. So the electronic transition timescales become comparable to the nuclear motion timescale. So you can no longer say electrons are fast and nuclei are slow. So they are both commensurate and they exchange energy. So you cannot solve this problem exactly, right? So that these intersections, they look like cones. They're called conical intersections. And we don't know how to obtain the dynamics here because the approximation is not valid, which means the theoretical methods are not valid. So we need to find a way to do this because it's a very important process. If you consider the photochemistry of vision, as you guys are looking at these slides, the photons from these slides are going into your eye. They're exciting some protein, rhodopsin, and then the protein and the electrons in that protein relax without emitting any photons. They relax by going through these conical intersections. Basically, the nuclear positions are changing and the electrons are giving energy to the structure of the molecule. So the protein is isomerizing along this coordinate because the electronic energy is being given to the atomic motions, right? And this is what then triggers vision, this isomerization of the protein. But the conical intersections are key to making that happen. Same is true in charge transfer. Same is true in the ways in which DNA protects itself from UV light. Because UV photon is very energetic and it pumps a lot of energy into the system. If you don't get rid of it, the bonds will break. So it basically gets rid of this energy by going through these conical intersections. So our goal was to figure out what is the strength of interactions near this conical intersection. And that's what we did. So this is an experiment where we created with an XUV pulse a hole in the sigma orbital of a CO2 molecule. And then what happens is that the hole moves automatically by itself into the pi orbital of CO2. And due to this coupling between the electrons and nuclei, they talk to each other and the energy is converted from one form to other. So we monitored this motion by creating this hole with one pulse and then ionizing the molecule and observing the ions with the second pulse. And then we could make these movies where we can track the electronic probability distribution as a function of time delay, which is being plotted here. And we found that whenever the charges move in the orbitals, the nuclear motions are triggered simultaneously. The x-axis here, one axis here represents the asymmetric stretch of the CO2 molecule, and the other axis represent the bend of the CO2 molecule. So what I'm saying here is that the charges move because the structure of the molecule is changing, or the structure of molecule is changing because electrons are giving their energy to nuclei. So this back and forth motion is what we observed. And so what I'll do now is that I can come back. I have like tons of slides on why this happens and what is the Hamiltonian for this system, but it's a tons of detail. What we want to do now is use the same methods, not for electron nuclear interactions, but for electron interactions, which are much faster, right? So in those cases, the same kind of thing happens. When you excite or ionize a molecule, you imagine that you're removing an electron from some orbital. Orbital is a nice construct, yeah, in chemistry. But in real life, with high energy photons, you don't remove electron from just one orbital. You create mixtures of different types of holes. So if you have 12 eV energy or 100 eV energy, when you look at what you have created, you will find that there is some amplitude for creating a hole in the A prime orbital, right? And some amplitude for creating a hole in the 15A prime orbital. So these two configurations are mixed together. Same over here. There is a mixture of those two different type of configurations. So as a result, what you get is a time scale over which the charges can adjust, because there is an energy gap here. And this energy gap corresponds to a certain time scale over which the charges can readjust themselves from one orbital to another. And this is an important problem where there have been a lot of theoretical predictions recently. How do the charges move from one end of the molecule to another? How fast do they move? And it seems like the time scales of motion are just few femtosecond or attoseconds, right? But then the question is, do nuclei play any role in it? Nuclei are heavy, they move slow. Should they play any role in this fast motion of charge from one end of the molecule to another? And the theoretical predictions seem to say that yes, they do play a role, but it's a negative role in many cases, that the oscillation of charge back and forth between the orbitals can decay, and the coherence can decay due to interaction with nuclear degrees of freedom. So it has a negative impact on the charge migration within the molecules. So these are the questions which need experimental verifications, which is where we want to develop X-ray tools to test this physics. What is the motion of charges due to electronic correlations, and how do nuclei impact that kind of motion? Now, this problem is very similar to the CO2 problem, which I talked about, where we monitored the motion of charge from one orbital to other, except we have to do it on much faster timescales. Now, this timescale is an order of magnitude faster than this timescale in our earlier study, right? So to do that, we are going to use X-rays. X-rays give us a beautiful advantage that each atom has its own unique absorption signature. Carbon absorbs around 280 eV, 290 eV. Nitrogen absorbs around 400 eV. Oxygen absorbs around 500 eV. So if we do spectroscopy with X-rays, not only we will get attosecond resolution, but we will also know which atom the charge is on. If this is my nitrogen atom, I can I can shine my light on this molecule, and whenever charge comes here, I will see that these orbitals fill up, and then these transitions shut off. So by monitoring the absorption as a function of photon energy and time delay, I can figure out the motion of charges inside the molecules. So our goal is to do this using two methods. In my lab, we produce these attosecond pulses through high harmonic generation. And the idea there is that, so now we are going to techniques, okay? So how to do the science, we need these techniques. So one idea is to basically use a laser pulse and ionize the gas. When you remove an electron from an atom, it's driven predominantly by the laser field because it's away from the influence of the Coulomb field. Now the laser field is what's driving the electron, right? So it's driven by the laser field, but the laser field is sinusoidal. Laser field oscillates up and down. So the laser field can drag these electrons away and also bring them back to the atom. And when this trajectory returns back to the atom, this electron collides with the atom. It produces this Bremsstrahlung radiation, this X-ray light, because of this high energy collision between the electron packet and the core ion that's left behind. So this is a well-known process called high harmonic generation. The reason is that this process occurs every half cycle. The laser field changes its sign every half cycle. The electrons keep going out, coming back. And one half cycle is 1 femtosecond. So these bursts of radiation that are produced are less than that 1 femtosecond duration. So these are attosecond bursts. And you can play tricks to make a single burst, and then you can push it also to very high energy region by using a longer wavelength lasers, which means you take the electron out farther out and then bring it back with more kinetic energy. So this is an experimental spectrum by Jilla group where they show that you can produce X-rays all the way up to keV using this process. So this is a setup that we have built in my lab, and we are working towards starting experimentation with that. And at the same time, just to put things in perspective, we are building CXFEL here, right? So this is source in my lab, costs about $1 million, produces attosecond pulse, but produces very little energy in each pulse. You can go to LCLS, which is a huge free electron laser. We go there, Sam goes there, Robert, you go there. People go there and do their experiments, but you don't get enough beam time, and it's super expensive. It's billions of dollars, and but it has tons of energy. So CXFEL lies in between. Yeah, the cost is in between, and the pulse energies are in between, which means we can do much more science than tabletop sources, and it can be much more accessible than large facilities, right? So we want to do the same experimentation with CXFEL. We will bring one attosecond pulse. We will bring one light pulse to create excitation inside the molecule. We'll bring an X-ray pulse to probe where the charges are. We will do transitions from core levels to the different orbitals and see where the charges reside as a function of time delay. And we hope to build spectrograms like this, where we can see that as a function of time, the absorptions are changing. And from that, we can infer how the charges move, and then we can compare with theory. So as a part of this effort, and I'm basically towards the end of my talk, we have this AMO end station planned at the CXFEL, and it has several components here. I won't go through the whole detail, maybe another time, but there are two end stations, one to do spectroscopy of photons, one is to use charged particles to do spectroscopy, right? So we will build these two end stations, and it'll be good to interact with folks here to do experiments with these end stations. So with that, I think I'm on time. I can start summarizing. I told you guys mostly about how we can use light to control the dynamics which occur inside atoms and molecules. I also showed you that we have done work where we can measure evolution of charges inside complex systems by using pump probe spectroscopy techniques. I didn't go into details here, but the future is here, how to figure out the attosecond dynamics driven by electronic correlations, how we can monitor it with the pump probe schemes. And if we do that, if we understand the control of motion of charges, if we understand how charges interact, electrons interact with nuclei, we can hope to apply this knowledge to systems of practical relevance, light harvesting systems, interfacial chemistry, photocatalysis. We can then use light to either control those dynamics, or at the very least, we can find ways to measure those dynamics and maybe devise ideas on how to improve the efficiency of those processes. So I'd like to thank folks in my group who did all this work. If you want more details on our work, you can go to my group website or scan this barcode here. Would like to also thank the funding agencies and the taxpayers for supporting this effort. Thank you so much.